Hi everyone, today I'm going to give you a quick rundown of some of the work I've been doing trying to model the interactions of radar waves with snow on sea ice. The work is motivated by the uncertainties present in sea ice thickness estimates from the Cryosat-2 and Altica satellite missions, some in situ radar measurements that were taken on the Mosaic expedition, and the potential future launch of the Crystal satellite altimeter that I'll come back to a bit later. Because this work is motivated ultimately by sea ice thickness retrievals, I just want to quickly recap the way in which we get that out of altimetry data. Satellite altimeters crisscross the Arctic Ocean and can measure the height of the sea surface at gaps in the ice. They also fly over the sea ice and can measure the height of the tops of the ice floes. We can then calculate the local difference in those heights, which is a quantity we call the freeboard. Because we know how much of the ice floe typically protrudes above the water, we can use the freeboard to estimate the total thickness of the ice. That's complicated slightly by the fact that snow sits on the surface of the ice, but it's not too difficult to adapt our formulas that convert freeboard to thickness for the weighing down effect of the snow. But the important thing is that we know what we're looking at. So we need to know whether we're measuring the height of the snow surface above the sea. That's historically what we've imagined Altica to be doing, or whether we're looking through the snow and measuring the height of the ice surface above the sea. And that's what we conventionally imagine Cryosat-2 to be doing. Why do we think that Cryosat-2 can see through the snow and Altica can't? It's because Cryosat-2 operates in the Ku band of the microwave spectrum, with a wavelength of just over 2 centimeters, whereas Altica operates in the Ka band, with a wavelength of 0.8 centimeters. So in the same way that your phone's 5G signal can penetrate through a wall, but your TV remote can't, Cryosat-2's longer wavelength Ku band radar waves have historically been assumed to penetrate the snow, whereas Altica's radar waves haven't. One question you might reasonably ask, and many others have, is are these safe assumptions that Ku band penetrates the snow but Ka band barely does? There's been quite a lot of research on this, but the field remains active, not least with our Mosaic project, which Rosie is going to tell you about in a bit. But that's not the topic of my talk today. The question I've been asking recently is, do the empirical properties of snow flow from physics-based modelling? So if we had perfect models but no in situ measurements, would we still be able to predict Ku band penetration and Ka band blocking? One obvious and crucial point here is that the truth that we're trying to model is still unclear. Up until now, with the exception of some in situ data collected by Rosie, we've generally lacked the ground truth data with which to evaluate the operation of snow radar models at Ku and Ka band frequencies. That's something that our Mosaic project is hopefully going to help to solve. But for now, we're simply looking to get in the right ballpark, and we found even that pursuit pretty challenging. So before I go any further ahead, I just want to introduce a couple of terms: surface scattering and volume scattering. These terms and this delineation comes to dominate the modelling approach. Surface scattering occurs when a radar wave encounters a macroscopic material boundary. So materials have this property related to how easily the electrons are moved around, called their dielectric permittivity. When a wave hits a boundary in this property, in general, part of its energy is transmitted and part of it scattered. So that's just what's happening at the one-way glass in the airport. Some of the light from your side is transmitted through to the people in the security office so they can see you, but most of it's reflected or scattered back at you so you can't see them. So surface scattering at the air-snow interface is what we've generally assumed to be giving us our Ka band Altica return, and surface scattering at the snow-ice interface is what's historically been assumed to give us our Ku band Cryosat return. The angular distribution of this scattering is quite sensitive to the roughness of the surface. For a smooth surface, like the glass at the airport, we get a mirror-like reflection. That means the angular distribution is like a delta function. For an electromagnetically rough surface, we get a much more isotropic distribution of scattered energy. That's like if you're looking at a wall or a matte object. This turns out to be a really important a feature of altimeter frequencies, and I'll come back to this in a second. We also have volume scattering, which is the scattering of radar waves due to the snow microstructure itself. That's represented by number 2 on this slide, and this scattering mechanism becomes increasingly dominant at higher frequencies like Ka band, when the size of the snow grains approaches the radar wavelength. It's this scattering mechanism that in part attenuates the energy of the wave once it penetrates the snow surface. The potential exists here for multiple scattering, that is, successive scattering of the same radar photon before it returns to a receiver. This has generally been neglected, but becomes increasingly important at higher frequencies. So how are we actually going to model the radar backscatter from snow on sea ice? We need a physics-based model, and to do this I'm using the SNO Microwave Radiative Transfer Model, which is a recently released open source model written in Python. It's a multi-layered scheme and it's very versatile and allows us to represent the snow sea ice system in a sophisticated way. For example, first year ice can be modelled as a bunch of brine inclusions in a saline ice matrix, whereas multi-year ice, which has been flushed by meltwater in the summer and has a lower density, is modelled as air inclusions in the same saline ice background. These inclusions can be spheroidal or needle-like, and we can put things like an ocean substrate under thin ice to improve the boundary conditions of the system. The model handles multiple scattering, so it can accommodate photons that return to the receiver after being reflected from the snow-ice interface, and then subsequently being volume scattered. And as I said, that's generally been neglected, but it's playing an increasing role at higher frequencies. Modelling volume and multiple scattering correctly is also really important if we want to generate insight from the polarization of the radar returns, but I'm not going to talk about polarimetry too much here. SMRT also handles the effects of dense media scattering in a state-of-the-art way. It turns out that the scattering power of a lump of snow can't just be approximated by a superposition of lots of individual snow grains with individual scattering powers. Snow grains are packed so close together that if you polarize one with a radar wave, its polarization is affected by its proximity to the others, and we need to take this into account, and SMRT does this. So those are some of the benefits of SMRT. But one significant drawback that we're finding to be consequential is that SMRT can't simulate the response of the roughness of the snow surface. This means that radar returns from surface scattering aren't fully realistic because the angular distribution and magnitude of the reflection and transmission is governed by assuming the snow presents itself to the radar wave as a smooth surface. To give an optical analogy, we're modelling the snow surface as a radar mirror with some transmission, when actually it's more like a highly reflective matte piece of paper where some light shines through. This modelling approach would work well at operational frequencies of older satellite missions like L-band, C-band and perhaps X-band. At these longer wavelengths, the snow presents itself as electromagnetically smooth. Unfortunately, at higher frequencies, the snow transitions to being electromagnetically rough, and this is basically causing problems. If we include roughness in our radar models of snow, we're arguably opening a Pandora's box. If we include it, we have to parameterize it, probably with at least two quantities, and the quantities involved are highly uncertain even when measured in situ, but even small uncertainties can have significant effects on the surface scattering properties. I just want to quickly draw a distinction here between the effects of microscale snow roughness on the backscatter and large-scale roughness of the system. Quite a lot of work has been done on the effect of large-scale roughness on the ice surface, large-scale roughness of the ice surface on the impulse function of a radar pulse. That's critical to understanding how we retrack the radar pulses as they return, so we can ultimately map a single time of flight value onto a waveform that's distributed in time. This is determined by roughness at the scale of the satellite footprint, which is several kilometers. That's not what I'm talking about here. What we need to do in this case is model the RMS height and feature correlation length on the scale of millimeters to centimeters, because that's the typical wavelength that we're dealing with. This is likely a function of the snow microstructure, and characterizing microscale snow roughness is really difficult, and it represents a significant frontier in cryospheric remote sensing. So to summarize our modeling so far, SMRT currently underestimates backscatter due to the lack of rough interfaces by at least an order of magnitude. This is likely due to inadequate representation of surface roughness. Because of this, we're seeing most of our Ku band energy return from the ice surface. You might argue this represents reality, but it also turns out that this is the case with Ka band radiation. Our model's snow just isn't visible enough to radar waves. So where do we go from here? We have a potentially very long satellite record of sea ice thickness from ERS-1 to Envisat and Cryosat-2, the family of Ku-band radar altimeters, but we'll only be able to fully interpret these data if we understand what we're looking at. Are we in fact looking at the snow-ice interface or somewhere above? If so, what dictates the height of the scattering horizon? Is it liquid water content of the snow, its microstructure, or some factor or combination? You might say that we could answer these questions with in-situ investigations, and that's certainly underway, but if the answer is indeed a complex combination of factors, and I suspect that it is, the best case scenario or holy grail would be to model the height of the snow scattering horizon based on snow models and reanalysis data, and that would help us better retrieve sea ice thickness. Before we do that though, we need to improve our models significantly, particularly in the domain of roughness parameterization. This is currently being done by SMRT's core developer, Ghislain Picard. I recently ran the development version of the model, and preliminary results indicate that backscatter is significantly increased at Ka and Ku band frequencies by incorporation of rough surfaces. Finally, let's just look a bit forward in the shorter term. A dual Ka and Ku band altimeter mission is one of the high priority candidate missions under consideration by the European Commission for inclusion in the next phase of the Copernicus space programme. A better theoretical understanding of how the satellite's radar waves would actually interact with the sea ice surface would significantly improve the value of the mission. If we can move beyond assumptions that Ku band radar penetrates snow and Ka band radar doesn't, we stand to improve the accuracy of sea ice thickness retrievals, but also access new and perhaps unexpected insights from the data. Thanks very much.